Hello and welcome to Lesson 25, and our topic today is continuous probability distributions. Continuous probability distributions. And the goal. So once you go through the note and you do some of the homework, you can identify the appropriate time to use and successfully apply a continuous probability distribution. So today, what are we looking at more specifically? So in the previous notes that we've gone through in this Unit 4, we've looked at a uniform distribution, binomial, geometric, hypergeometric. And what we say, they always deal with discrete data or integer values. You couldn't have 0.3 of a person, you couldn't have 0.7 of a sock, or same thing with fish, you have to have whole fish. So we're dealing with discrete values. What happens when we no longer have any discrete values? What happens if we have to start applying decimal values? So continuous distributions deal when decimals, and that's rational or irrational numbers, are possible. Okay? So continuous probability distributions are graphed with a smooth curve rather than a bar graph. So up to this point, you were using a bar graph, and I'll just show it up here, I guess. Okay, you're having the computer software, or you were doing it manually, whichever method you were using, and this is how you were doing your distributions. Now, so that was for discrete. When we move to continuous, we're no longer going to use bar graphs. Okay, so in this case, we're looking at continuous, and it's going to look something like that. So now we're going to use that smooth curve, and I'll show you where that option is, or you're just going to manually do it depending on what application you're doing here. All right, and to finish this introduction off, so in this lesson I'm going to focus on the characteristics. So I'm just worried about the characteristics of a continuous distribution, and I'm going to introduce something called probability density. Okay? Probability density is kind of the whole point of the remaining lessons here, and that's what our focus is going to be on. So population density, it's represented by these distribution curves, and this is what I'm talking about. When I refer to a distribution curve, this is what I'm talking about. That's our distribution curve. Very similar to a frequency diagram with discrete data. The difference is it's a smooth curve, and a couple new properties arise from it. We're going to talk about that. All right. So first of all, a couple of common types. There's three common types of continuous distributions, and I just want to talk about them briefly. So the first one is what we call a positive skew. And I didn't do a very good job drawing a positive skew. So positive skew looks like this. And I'll let that fade, and I'll draw in the permanent pen. So a positive skew is when the hump, believe it or not, it's the actual terminology, it's when the hump is left of the mean. So when you go ahead with a set of data and you calculate the average or the mean would be right there. However, our hump is to the left of that data. So positive skew. That's when hump is left of the data, of the mean. All right, so that's what we call a positive skew. So even though when you calculate it, the mean occurs in this location here, the actual hump, or the most frequent, is right there. Which brings me to negative skewing, and that one looks like that. And most of you got that figured out, or what your expectation is there. So our hump is now to the right of the mean. Okay, so a negative skew when hump is right of the mean. Okay, so there is your two types of skewing. Now, Maybe I should add in here, and it comes along in a later lesson, so it's not cloned. I'm just going to copy that. If you want to just give yourself a quick grid, very similar to what's there. I just want to tell you, or explain what's it compared to. Okay, so when we're talking about this skewing, the skewing is compared to what we call a normal distribution. And a normal distribution is when the mean and the hump line up. Okay, so the two above, the positive and negative, are compared to what we call a normal distribution. So a normal distribution when the mean and hump are located at same value. So that's what the top two ones are compared to. All right. So that's where the comparison is. We're making a comparison to our normal distribution. All right. So there is that, and this is what we call unimodal. Okay. One mode, and in brackets, it's located at the hump. All right. Similar to your frequency diagrams from discrete data, we have unimodal, which means that our mode is occurring. There's where our mode is. There's where our mode is. So there's only one mode. And same thing in the normal distribution. There's our mode. So they're all located at the hump. And that's unimodal. So when we move into our last one here, the bimodal distribution, this is when you end up with a double hump. Okay. And we have two humps in this case. So bimodal, which means two modes. That's how it comes up with. Bimodal distribution. When two humps occur, when two humps occur, and what happens is it means your data is kind of split here. We've got two groups within that group, so the data is very split. I don't know if I really need the word very, but it's split. Okay, so really what you end up with, you have essentially two groups of whatever people. If you want to talk about in terms of a class, you have one portion of the class that has absolutely no idea what's going on, and then you have the other half of the class knows exactly what's going on, and there's really no one in the middle, no one kind of knowing. Okay, and that's where you get with those distributions back here. If it's, you know, here we have the majority of people, and this is a reference to class marks, if you want to look at it that way. We have a lot of people that know what's going on, or in this case, the majority of the class is below the average, so not a whole lot of understanding. And then this is the ideal distribution where most people know mostly what's going on. All right. In this situation, this is a bad situation because you got two sets of data that seem to be distinct from each other. Okay. So there is your bimodal. Now, I would just want to talk about, and here's the trickiest part when dealing with continuous distributions. It's a density, population density. So here is the shift in thinking when we're dealing with a probability distribution. Okay, so I'll give yourself XY axes here and give yourself a graph, something big enough that we can draw under. So the concept of population density, we're moving away from frequency being on the y-axis. So it's no longer frequency on that y-axis. What we're looking at, population density, or the sorry, that should be a probability density. That'll make a lot more sense. Probability, thinking geography, probability density. What happens now is that the probability is the area under the curve is our probability. So area under curve is equal to probability. And that's the trick here. So when we're talking about the questions in the upcoming or the final few lessons here, we're going to be looking for area under curve. And with a continuous distribution, like we have here, that area under the curve is equal to our probability. So we're finding area under the curve. How are we going to find the area under a curve? Because it's not a rectangle, and to find that area, it's kind of tricky. You don't have to worry about that. I've got a chart that has all that taken care of. So there is the tricky, this is what you got to wrap your mind around in this particular end of this unit, is that probability is the area under a continuous continuous distribution. All right, we'll finish this note up with the next example.